At a distance of 2.5 million light-years, Andromeda is the closest galaxy to our home galaxy, the Milky Way. Light emitted from our radiant neighboring galaxy therefore takes an unimaginable 2.5 million years to reach us. Since nothing and no one can travel faster than the speed of light, it seems impossible that any human will ever be able to travel there within their lifetime. That is a crushing realization, especially when you consider that even this distance is still just a vanishingly small fraction of the entire cosmos. And it forces us to face the uncomfortable reality of how truly isolated we are. But physics doesn't make it quite so hard for us. Even though light needs millions of years to cover this distance and nothing can travel faster than it, it is still possible to reach the Andromeda Galaxy in just 10 years. How can that be? One of the fundamental insights of Einstein's special theory of relativity is that the speed of light is the absolute speed limit in our universe. Nothing and no one travels faster than light. Since distant stars and galaxies are several million to billions of light-years away from us, one might assume that this speed limit makes any kind of intergalactic travel impossible. Because at a distance of 2.5 million light-years to the Andromeda Galaxy, even at 99.9% of the speed of light, it would still take about 2.5 million years to cover that distance. This, of course, far exceeds the lifespan of any individual human, and even of humanity as a whole many times over. But if we analyze the situation more closely, we realize that the speed of light as the universe's speed limit is more of a blessing than a curse for intergalactic travel. For as Einstein proved, relativity not only implies the speed of light as the absolute speed limit, but also the contraction and dilation of space and time. That means first, moving clocks run more slowly. If we see a clock fly past us, then from our perspective that clock ticks more slowly than for an observer moving along with the clock. Secondly, distances appear shortened for a moving observer. If a fast car drives along a racetrack, then from the driver's perspective the track appears shorter. Einstein first proposed these claims in 1905, and over the past 100 years they have been confirmed by countless experiments. How strongly space and time are distorted depends on how fast observers move in relation to the speed of light. Einstein managed to derive exact formulas for calculating this distortion of space and time, and his equations tell us the closer the relative speed of the observers is to the speed of light, the stronger the distortion of space and time becomes. At our everyday speeds, such as in road traffic, however, this effect is so tiny that we cannot perceive it. Light itself can move at 100% of the speed of light, but no object with mass can. So let us assume we had a spaceship that we could accelerate to 99.9% of the speed of light. This is technically impossible today, but from a purely physical point of view, it would in principle be possible to build such a spacecraft. Then it is very easy to calculate that this spaceship would take about 2.5 million years to cover the distance from here to the Andromeda Galaxy. But this result only applies for one observer. Those 2.5 million years only pass from the perspective of stationary observers on Earth. If we instead use Einstein's formula to calculate the time on board the ultra-fast spaceship, we find something astonishing. Time slows down so enormously at 99.9% of the speed of light that while 2.5 million years pass on Earth, only about 10 years pass on board the spaceship. Thus, in principle, it would be possible to travel to our neighboring Andromeda Galaxy and back to Earth within the span of a human lifetime. This also makes a substantial difference for the spacecraft's equipment. It would need to support the crew for a decade, rather than sustain a species for millions of years. So if a spaceship could get close enough to the speed of light, the time contraction for its passengers would be so enormous that virtually any distance could be covered in a very short time. But there is still a catch. If one were to undertake such a journey, one would have to leave life on Earth completely behind. For although we could cover astronomical distances within just a few years, time on Earth would continue to pass entirely normally. If, for example, we were to travel to the Andromeda Galaxy and back within 20 years, then 2.5 million years twice over, that is 5 million years, would have passed on Earth. Upon our return, humanity would either have gone extinct or reached a completely new stage of civilization and evolution. In any case, after an intergalactic journey at near light speed, we would not find the Earth as we had left it. Thank you for watching.